And thank you, everybody that is here today. Good day to everyone. As Sarah mentioned, I will be doing the presentation of the tropo scatter effect with tropolinks in SpectrumE, and hope that I can spark some interest for you guys that are in the GoToMeeting here to start using our tool and using the TropoLink object to run simulations on your side. For those that have access and those that don't, that you may ask for a trial or acquire a subscription. So I will go now into the presentation. So SpectrumE, it's a spectrum engineering tool. It's a cloud-based integrated solution that we've developed at Spectrum Center. And for today's presentation, I'm going to be talking about our implementation of the ITU-R P.617 propagation model for designing planning of tropolinks. For those that are just getting into tropolinks and may not be familiar with their topology or typical applications, I'm going to start out with this part. So basically, tropolinks are mostly used by military entities where they have a need to deploy long distance communication links. And it may happen that they may have access to an island and may want to reach the mainland. So you have that example, and that may span over, say, 300 kilometers, 400 kilometers. Or you may have a long distance communication that you need to establish that has a lot of mountain terrain in between. So as you know, typical line of sight applications will not work, like microwave links, for example, as they are line of sight technologies. And any obstruction in the terrain will obviously block that communication. In tropolinks, however, the use of the troposphere is made so that communication can be established by the reflection, deflection, refraction of the signals from the troposphere, as well as other propagation phenomena that I will explain and go over in a little bit. So this is a screenshot of some of the examples of some links that I have, and I will actually, towards the end of this presentation, show you a little live demo with the same network that I'm showing here. Some of the capabilities will allow us to do what we call a keyhole coverage for these tropolinks, so that the users may know exactly what is the power received at every pixel around the intended receiver. We have legends that are customized by the user on the left side, as you can see here on the map. The tool is a module-based access. It has different modules. So in the one that I will be presenting to you and the one that has the TropoLink object is the engineering module, as you can see here. And the way to access it is through this module. Once you go in the tool, you're able to either create your TropoLinks one by one using generic forms, or you can batch upload through CSV and then start designing and planning your tropolinks. Here's an example of one of the reports. It's a path profile report for the tropolink. And as you can see here, you can see it's 344 kilometers in distance. Of course, the Earth curvature is large. As you can see, line of sight technologies wouldn't work for this link. And you can actually see the takeoff angles, the common volume, and other features that are related to tropolinks, and I'm gonna go over those in a little bit. Another method to access this capability for tropolinks is through an external access to our API. And here, users can implement in their own client software calls to our API server and get returns such as path loss, link budget information, path profiles for a given link, one at a time or in batch. Now we'll go on to the propagation mechanisms. There's two main ones that are of interest for transhorizon communications. So these links are typically above 30 megahertz and into the gigahertz range. And what you will be mostly interested is the diffraction and the tropospheric scatter effect. Of course, there's other phenomena such as ducting and layer reflections that can occur. And they are covered in the ITU-617, but they're secondary. The primary diffraction mechanisms are diffraction and troposcatter effect. And as a side note, the ITU-617 calls the ITU-525/526 for the diffraction mechanism. And that's this one here in the middle that you see with this line labeled as diffraction. For the troposcatter effect, of course, we use the ITU-617. And for previous mentioning of line of sight technologies, as you can see, there's one example here. When you do have line of sight technologies, typical for microwave links. Of course, those are for shorter distances. Other propagation mechanisms that are included in the 617 are tropospheric, the ducting layer reflections, the hydrometer scatter, as you can see here with these lines. Something that is of interest with the hydrometer scatter is that when the signal goes to a high concentration of rain in the middle of the link, the signal gets reflected off the water or the droplets in a sporadic format so that they could actually even come back or reflect in different ways, not necessarily on the same manner as the tropospheric effect that I showed in the previous slide. So you can have constructive or destructive reflections coming to your receiver in this case, and there's a high amount of measurements that were done regarding this effect. And it's very important because typically for line of sight technologies, what is found is that the rain and climatic effects has a very negative effect on your signal being received. However, with the measurements and the examples provided from the ITU, it was observed that in the common volume, where this is the most important region for tropolinks, which is over here in the middle of the link, when there's a high concentration of rain in that area, then the signal that gets reflected is actually enhancing the received signal most of the time. Therefore, when users think of the worst month concept in regular point-to-point links, they automatically see the worsening of the power received. However, in tropolinks, there's actually a little enhancement. And there are various examples that are provided, and again, with measurements from the ITU for this. And this is also covered. Now, all of this has been implemented with the, in terms of the climate, with the ITU 841, for those that are interested in those references. And they are also mentioned in the ITU 617. Now, I keep speaking a lot about the common volume, and as you can see, the distance of the links and so forth. And there's a reason for that, because that is very, very important for tropolinks. The geometry is more complex than it is for regular microwave links or other point-to-point technologies that are based on line of sight. For tropolinks, the tool automatically extracts the terrain profile along with the clutter layer information, along with another layer called the radioclimatic zones. And all of this has to be in the tool, and it has to be precise, and it has to be according to the recommendations from the ITU, which come from the ITU 452 into how to implement these layers. Now, once all of that is extracted into memory in the tool, the angles are calculated, which you see here. The three main ones are your transmitter takeoff angle, receiver takeoff angle, and out of the terrain geometry with the distances and those angles, we finally calculate the scatter angle. Now that is super important because that is the angle that determines where your signal will be reflected off the troposphere into your receiver in the direction of the takeoff angle from the receiver. Now, how these takeoff angles are extracted from the terrain is also key. There's various algorithms implemented in the software that does this. And it's looking at every pixel along the terrain and finds the first pixel where the first occurrence of an obstruction due to the first obstacle occurs. And that is what is depicted with this line here, with this arrow and this peak. So we find this point for the transmitter side, and we find the other point for the receiver side. And at the intersection of those two line segments, that's where the scatter angle is constructed in the path profile. And from there, and that is the region, this is where the most optimum reflection point, right, of the troposphere is at this scatter angle. However, it's not just a precise line. That's for drawing up the geometry on the left side. On the right side is what you actually experience in real life. So in the real life, this scatter region is actually bigger and is more like a polygon, as you see here. And so this region is called the common volume. So that's very important for TropoLinks. In this common volume, anywhere inside the inner polygon, that's where the signal will be most reflected of the troposphere into the receiver with a higher signal strength. Of course, you also have other regions where this effect may occur, but the main one is the area of the common value at the intersection of all these two line segments from transmitter and receiver. And what I was mentioning about the method that the tool uses to extract the different layers that are built in the tool, we have the methodology from the ITU-R P.617-4, which is used for this. This is cited in section or chapter 2 of the ITU-R 617 for those of you who may be geeky and have knowledge about software or implementation for these recommendations. That is the reference. Now, this is very important as well. Even if you have everything else, if you don't have this, you don't have a tool to model tropo links. The reason why this is so important is because these are actually digital maps that are provided in the 452, and they come in zip files. And these vertical maps, digital maps, have to be implemented into the tool to extract the vertical variation of the radial reflectivity and surface reflectivity values. That's the DN and DN values that are mentioned throughout both of these recommendations for those of you that like the formulas. So to extract this appropriate value, the tool has to read these maps along with the coordinate information provided for the tropo links. It's also very important because in some legacy propagation models or proprietary models used by other softwares and so forth, they usually allow users to input just one value. And that's the value that is used for the whole software. And sometimes it may be used for the whole world. And of course, that would be wrong. As you can see here in the map, depending on the region of the world that you're in, and of course, the length of your link, your values will change. So it's important that this is implemented properly. And we made use of the previous implementation that we had in the software for the model ITU-R P.617-4, where we ran extensive validations comparing it to the example measure results from the ITU. So we have an exact match with the ITU's supplemental files. And another layer that is very important also to be able to model tropolinks is the radioclimatic zones. So here I'm showing an example of different colors. So you have the inland areas, you have the coastal areas, you have, of course, what is water or oceans, sea. So those three classifications are part of a separate layer that is used along with the clutter. And the clutter for us, it means everything that is on top of the terrain, like trees, for example, urban areas, and so forth. So all of this together is used to determine those takeoff angles that I talked about before. And these radioclimatic zones also are very important because they do help determine the portion of the link that is over land, the portion of the link that is over water or coastal areas. And a ratio is formulated. From this ratio, the tool is able to automatically deduce the appropriate conductivity and permittivity properties of the terrain to use in the calculations. Now, this is very important because like I mentioned before, or maybe other legacy tools, they may ask the user for such values. However, from a human perspective, a person doesn't necessarily know what the conductivity or permittivity value is, say in California area versus the sea in the Pacific or Australia and so forth. These values change. So depending on the type of terrain, like I said, maritime over sea, maritime over land, I said average terrain, desert, so forth. All these type of questions are usually asked of the user and lead to a lot of errors. However, in Spectrum E, we're using the algorithms from the ITU-617, which calculate these values automatically from the coordinates of the system and where they're located on the Earth, and of course, how Spectrum E extracts this data from the implicit cartographic files that I mentioned, such as this one, the radioclimatic zones. And here we have a typical map view for a typical TropoLink design. This coverage that you see here is very important. I can show you how to generate one in a little bit when I show you the live demo. I just want to go over some of why this is useful and why we've implemented it in this way. So for typical point two areas, people usually think of coverages as a circle, 360 degrees, you see where you have service. However, for point-to-point technologies, we've developed our own keyhole coverage capability. And what we mean by this is if you look at this coverage, it looks like a sector, and it comes in two formats, a 10-degree span from the center of the link or 90-degree span. This is a 90-degree one, so it's a little wider. 10-degree one would be more directional, like a more directional sector. The reason why we do the keyhole, one is to optimize the time in calculations of such coverages. Of course, some links may be 600 kilometers, so you definitely don't want to spend a lot of time running at 360 degrees and looking at a coverage in the back where you have no interest. But where the interest lays is right at the receiver. Why? Because when you're deploying the systems, your intended receiver, you want to know where to put those receivers, right? The intended receivers. So the software helps you to determine how many kilometers, let's say to the left, to the right, or back, that you can actually move your receiver to in order to receive a better signal. So if you have a color on this propagation plot that is higher in field strength, you can actually pick up the receiver and move it to where you have a better signal reception and hence improve your signal. So that is the main reason why we've implemented the keyhole. And it automatically picks the distance to calculate also from the distance and the coordinates of the link. And because it is a link, you run the coverage for either point A, so that will be your transmitter, or point B, your receiver. That way you can see if you want to move your transmitter or if you want to move your receiver. So here we have the form where you can input the technical information for your TropoLink and how you can generate your path profiles. So once they're created, just pick one, select the path profile function from the left, and you're able to see those 2D profile views. And another reason why it's important to have the appropriate terrain information in the tool is because if you don't, you might not be able to get a real life takeoff angle calculated in the scatter region and so forth. So you do want to have a good resolution in that terrain, that you're able to see the obstacles, to calculate diffraction if you need to, and so forth. Another useful feature of the tool is the ability to generate 3D plots from those cartographic files that are stored in the system. And you can see why it's very important to use these TropoLinks for long distances, especially when you're traveling across mountain ranges from this picture. All right, and now I'm gonna go to the live demo and show you a little bit how we use the tool for these links. So as you can see here, I'm live in the application. This is our production server. You can reach it by going to spectrum.center in your URL bar. And here's various TropoLinks across the US. Actually, I do have many scattered throughout the whole world for this network. And I'm gonna show, I was logged out. Let me log back in. I'm gonna show you the network topology here. So we have different radio object types. And I wanna go to the TropoLink object. So I have over 700 links. These were all real links that were used with the Department of Commerce and the NTIA for the purposes of running measurements and comparing it to the simulations that were being produced at that time to develop the algorithms that were used to create different propagation models. There's many legacy models that were created, different versions and so forth. The original work from this effort was reused in the ITU-617, and it's also mentioned in the ITU Radio Handbook for troposcatter links. So in here, if you look at ITU-617 version 1, you will find the example for this link in Japan. So I'm going to show you that one real quick. And here it is. And I've enabled the labels for that link just because it was mentioned in that version of the tool, of the recommendation, sorry. And I'm gonna generate the path profile for that link. And here we go. As you can see, it's very user-friendly. You see the takeoff angles, or the link budget information is towards the bottom. There's legends, power receive, threshold values, model losses, and so forth. If you want to play with additional features such as moving around your technical parameters, such as antenna heights, for example, you can do them on the fly and recalculate the information. It generates a different profile view. And of course, the information at the bottom is changing, and you can play around and go back to the previous state of the path profile. And one of the nice features is that you can play around with that path profile without changing the actual parameters of the link. But if you wanted to, you could by simply going to the form and editing the files there. Now, we have the keyhole coverage calculation. So if we do this, I'll leave it by default. And you have different options. Here you can select the worth month effect that I was explaining to you about with the ITU 841 as implemented in the 617. You have different clutter options. For example, considering the clutter at the receiver, transmitter or receiver, or you can choose to not use it if you want to. I'm gonna do a keyhole size of 10 degrees span to contrast what I showed before from the PowerPoint slide. And I'll run this coverage for the side A, the transmitter on side A. As you can see, it's pretty fast. When you are done, it refreshes, and then you can actually just go to the map. And from the predictions page, select that keyhole coverage. And when you go to the map, you'll see it. So as you can see, it's more directional than what I showed in the PowerPoint slide. And then you can zoom in to different parts, preferably around the receiver. And as you can see, when you move the map, when you pen the map and put the blue crosshair that you see in the middle, that determines the reference point for this coordinates at the bottom and the actual power received, in this case, negative 98.8 dBm. And if I go to where the receiver is, I can see here negative 98.3. So it's actually at a slightly better location than that first point that I picked. But if I go to another area, for example, like here, you can see here negative 115.2. So you can see from the map areas where you wouldn't want to move your receiver to, or areas that you would want to move your receiver to. And to move it, of course, you just hover over the receiver, and then going to object info, you can select to move the object as you want. And if there's multiple objects, you can move others. And that's how you can design, plan your links. And something that I wanted to show you too before I close off is the 3D path profile view. So this is a link in the or various links in the US. So as you can see, you have here a link that is going across a mountain range. So of course, microwave links wouldn't work, but TropoLinks would. And then you have a lot that are here, and users might say, hey, I have a flat terrain there. Why can I just set up a link, a regular link? And the issue is that these links are over, in this case, the bigger ones are over 600 kilometers. So just to give you a better eyesight as to what is actually going on, I do have one of these links that I put in a screenshot here, and and I can show you the earth curvature for these links. So they would not work with typical point-to-point line of sight technologies. And therefore, you do need the tropo scatter effect. So this is a good example, I believe, to show the reason why you might want to plan for with TropoLinks for this type of network deployments. And with that, I close the presentation and I leave it open in case you guys have any questions that you want to go over or anything interesting that you guys saw.
Thank you. Thanks for that, Joel. That's great. We have had a couple of questions come in, and I'll put you to in a minute. Anyone has any questions, you can put your hands up. I can unmute you and you can talk to Joel directly, or you can use the questions toolbar. So that's any questions via the audio hands up or the questions toolbar. While I've got your attention, Joel, we did have one come in, which was, can the takeoff value be changed?
Oh, yeah, that's very interesting, and that is actually very important. I didn't go over that, but we have a few minutes, I'll go over that. So there's different military documentation on this. There are tools that military uses to have measurements and have more precise information about the optimum angle to use. Sometimes it's not about the measurements, it's more about what has happened in the terrain, like in the last week, for example, or something like that. Did somebody put up a building or something like this, or is there like vegetation that was not there? So what they do in that case is they want the tool to simulate or allow the user to simulate changing the takeoff angles. So for that, I do have some path profiles. For example, I'll show you this first path profile is the regular one that I showed you earlier. Now the same link with a modified takeoff angle. So in here, you can see the model loss 209.6, and in here, 209.3. So it will change. It may not change much. It may change a lot. It just depends on the geometry of the terrain and the link information that you have. So in this case, it didn't make much difference. This line here, the first one, is the optimum takeoff angle as soon as it clears the first obstacles from transmitter to receiver to the scatter angle region. But in the event that there are maybe new buildings or something like this, or heavy vegetation that was not there, you didn't have the clutter information available for some reason, you can, in the link information in the form, change your takeoff angle. So if there is no value in the field, it will calculate it automatically. And that will be the value that you see in the path profile for the horizon elevation angle according to the ITU. Now, if you do change those values, like I did here in this example, I just went off a tenth of a decimal for A and also for B. I changed that as well. Then you can see that the information in the tabular format in the table here, it will give you the ITU auto-calculated value and the user customized values at the same time, so you can compare what you put in versus what the ITU is recommending. So you are able to do that. And it's very, very important to be able to do this. It's not in the ITU-617. However, in practical military deployments, when this is done, the vehicles are being moved in real time. So you may set up a link and move it, and you come to an area and the optimum calculated or recommended angle doesn't work. So then you have to have the ability to simulate another angle that gives you a better propagation model loss, or actually just gives you a signal, right? So this is a very good feature that we've added. It's an enhancement capability in the profile view that we have in SpectrumE.
That's lovely. Thanks for that, Joel. We have had another question come in here. What's the difference between this implementation and 617.5?
Yeah, so we implemented this with the -4 when we're usually customer driven. So when we have a delivery and we have a customer that is requesting this feature or so forth and requires an update, we give that, we expedite the delivery and implement that. However, there is a process where we update to the latest models, and we haven't gone there yet. The -5, I believe, came out like in November of last year. So we haven't gotten around to implementing the latest version, but we usually do when we have the time to do that. However, when we deliver the models, since they have been validated and they're working and they're validated with measurements, and the customer validates with other measurements or links that they have on the field, we don't tend to, we're not hasty to change the algorithms or the methods because they have already been validated. And sometimes with the updates, we do need to validate that there aren't any errors in the recommendations. In the past, there has been some errors in upcoming recommendations, which are fixed in later versions. So we do need time to validate those, but we haven't gotten around to do that yet for the -5 version.
That's lovely. Thanks for that, Joel. Okay, while awaiting for any other questions, just a couple of things to follow up from today's event. I will be sending you a survey. It takes 3 minutes to complete. They're really important to us. It helps us develop our webinar schedule and program, and it gives you an opportunity to influence that in the future. So there's something you want to hear about in the future, complete that survey, pop it in, and we'll make sure it gets fed back in to the future program. I have got a recording from today's event that will be sent to you in a follow-up email, and also an invitation to our next event. Our next event is being held on Thursday, the 5th of March. We'll cover correlation of measurement data within SpectrumE. This event will demonstrate the import of measurement data and the model tuning aspects that are available in the software and the outputs from that. So you get a first chance to early bird opportunity to register for that event. You'll also get a handout, which is the white paper as well. In the absence of any other further questions, I'd like to say thanks to Joel for taking today's event, and I look forward to seeing you guys all very soon.